Hello, dear students. Welcome you all. In this lecture, I am going to discuss about the Fermi-Dirac distribution law, right? Fermi-Dirac distribution law, right? Fermi-Dirac distribution law is basically the first step uh, in going into the discussion of Fermi-Dirac statistics, right? First of all, we will understand what is Fermi-Dirac statistics, what type of particle are covered in this branch of statistics, who developed this statistics, and then after we will drive a distribution law for this type of statistics, right? Fermi-Dirac statistics is a branch of quantum statistics, clear? Right? I told you earlier in the case of Bose-Einstein statistics that in quantum statistics there are two branches, Bose-Einstein and Fermi-Dirac statistics. So this branch of statistics was developed by Enrico Fermi and Pauli Dirac, right? In 1925-26. They developed a systematic theory for the treatment of a fermions particle, right? So this entire theory is called Fermi-Dirac statistics, and the particle that obey this branch of statistics, they are called as fermions. Clear? Right. Fermions, because they were Fermi and Dirac statistics, right? What are the examples of fermions? Fermions are all those particles which have a half integral spin, 1 by 2 h cut, 3 by 2 h cut, clear? So on. Example includes electron, proton, neutron, right? Similarly, quarks, clear? All these particles are example of fermions, clear? Now we are going to drive a distribution law, just like as we did in the case of Maxwell Boltzmann statistics and Bose-Einstein statistics, clear? We have seen that in case of Maxwell Boltzmann, it is Ni upon Gi is equal to 1 upon e raised to power alpha plus beta Ei, clear? Whereas in case of this, it is equal to Ni upon Gi is equal to 1 upon e raised to power alpha plus beta Ei minus 1, clear? So we are going to develop such type of a distribution law for this branch of statistics also. Once we will drive this law, then we can apply this distribution law to find out the different properties of fermions, right? Now I'm going to drive this law, right? So for it, uh, we are considering n fermions, right? N fermions. Now fermions can be either electron, proton, or neutron. Any of these particle can come in this category, right? And we are going to distribute these n fermion into the given space. Clear? So I'm going to draw it here. And let's take a big compartment, clear, in which we are going to distribute these n fermions, clear? Right. Here we have n fermions, right? N fermions, right? Now, before proceeding into all this discussion, we have to uh, took into consideration some postulates, some assumptions. So the first one is right. All the fermions, these particles are identical as well as indistinguishable. So we know very well in quantum statistics, the particle are identical and indistinguishable. The second postulate is as these particles are a fermion, clear? So they are going to obey Pauli exclusion principle, right? So they're going to follow Pauli's exclusion principle. What does it mean? It means only one particle can enter into one phase space cell. Clear? No more than one particle is allowed to go into each phase space cell. Right? So this is the restriction. Right? Third one is in this case, as it is quantum statistics, so the minimum volume of the phase space cell is again HQ. Here H is a Planck's constant. Clear? Right. Here H is a Planck's constant, right? So all these things has to be taken into consideration while we are going to make this distribution. The particle are identical and indistinguishable. Particle follow Pauli's exclusion principle. There is restriction on the number of particle entering in a compartment. The minimum volume of the phase space cell should be equal to or greater than HQ, right? Now, suppose at any time, right? All these particles will have different energies, right? So what I do, I separate all the particles having different energy into different groups. So in order to do all that, let's suppose that this entire system has some energy E, clear? And this is the energy to be distributed in this way, clear? This is the compartment where we are going to distribute this energy, clear? This is the total energy of all these fermions, right? Now, we are going to divide this entire given space. Now we will call it as phase space, allowed, momentum and position space. So now I'm going to divide it into the different compartments, right? Compartments of different energy range, right? So this is the first compartment. This is the second one. This is the third one. This is the fourth one. So on. This is the kth compartment, right? This is k minus 1, right? So all these are the compartments. This is first. This is first compartment. Clear? This is second. This is third. This is fourth. This is fifth. No, no, sorry. This is kth, and this is k minus 1. Clear? So similarly, we can take the other compartments. So what we did, we divided the entire given energy into different compartment. Compartment means different range of energies, right? Now, then what will be the next step? Next step is we have to divide all these compartments into small cells of equal size, right? But before that, let me make it clear that the energy corresponding to the first compartment is E1, corresponding to second is E2, corresponding to third is E3, corresponding to fourth is E4. Similarly, corresponding to this is EK, and corresponding to this is EK minus 1. So now we are going to divide these compartment into further small cells of equal size. Clear? So these are the cells of equal size. Now let in the first compartment the number of cells, such cells are Z1. Clear? Number of such cells are Z1. Let this is having number of cells Z1. Similarly, in the second we will have a Z2, Z3, Z4. Similarly, here it is ZK cells, ZK minus 1 cells. Right. So what we did, we divided all these compartments into elementary cells of equal size. Right. Such that the first compartment has Z1 cells, second has G2 cells, third has Z3, sorry, so on. Kth has ZK cells, and this has GK minus 1. Now, these n particle are to be distributed in these different cells. So here the problem is analogous to the distribution of n particle into k compartments, which are further divided into cells. This problem we have studied already in classical statistics, Maxwell-Boltzmann statistics. So here the problem becomes now analogous, right? Only difference is the particle are fermions, right? So different possibilities are there. Different number of particle can go in different compartments. So let's consider the one possibility among all those possibilities. In this possibility, the first compartment has N1, second has N2, third has N3, this has N4, this has Nk, and this has Nk minus 1 particles. So what we did, we consider only one possibility out of all those possibilities. I can say this is the N2 macro state, N4, Nk. Clear? So this is one macro state corresponding to the all possibilities for the distribution. Right. Now what we are going to do? We are going to do to find the thermodynamic probability. Right? Thermodynamic probability means the number of meaningful arrangements, right, in this kind of distribution for this macro state. This is the task. Clear? W is equal to W N1 and 2. We will write down the equation for this value of thermodynamic probability. Right? So for doing so, first of all, we will start with the first compartment. Right? We are going to consider only first compartment. Clear? So here I am going to consider the first compartment. Now becomes a bit dark. So right, this is I'm going to consider. Right. So the first compartment has a N1 particles and a G1 cells. Clear? So first of all, we will find a W for it. Clear? N1 Z1. Right. So then after we will apply this to the other compartments also. So here, first of all, we will find the total number of ways of arranging uh, N1 particles in a Z1 cells. Here one thing is very clear. As only one particle can enter in one cell, it means so the number of cells Z1 should be greater than N1. Either G1 should be greater than or maximum it can be equal. If G1 is less than N1, then the distribution is not possible. Clear? This was possible in Maxwell, Boltzmann, and Bose-Einstein statistics, but here it is not possible. So let's consider Z1 is greater than N1. So when we will distribute particles, let's consider we have 7 particles. I wrote them as 1, 2, 3, 4, 5, 6, 7. Clear? Not 7 particles, sorry. I have 7 cells. Clear? So I'm going to write these are the 7 cells of the phase space. Right. So these 7 cells are there. Suppose I have 4 particles. A, 4 particles. I gave them name A, B, C, D. Clear? Suppose these 4 particles A, B, C, D are present in the first 4 cells. Clear? Up to this. Clear? So the remaining 3 cells, 5, 6, 7 are empty. Clear? So if I look at the arrangement, right? Now this is the example of this arrangement. So it is clear from here that these 1, 2, 3, 4, 4 compartment can arrange themselves in how many ways? 4 factorial ways. But as the compartments are identical, particles are also identical. I have gave them name for my own convenience. So it means this arrangement is equal to meaningless. Clear? Similarly, the number of cells or compartment that are left empty, 5, 6, 7, if I rearrange them among themselves, then again that is meaningless. So it means 3 factorial. In this case, it is again equal to meaningless. So what is 4 factorial? 4 factorial means that is n 1 factorial, number of particles. And what is 3? That is 7 minus 4. That is G1 minus N1 factorial. So this is the total number of meaningless arrangements. Right. Total number of meaningless arrangement I have found, that is n factorial multiplied by G1 factorial minus N1 whole term factorial. Now what are the total number of arrangements? Now as there are 7 possibility, 1, 2, 3, 4, 5, 6, 7, 7 cells are there. So these 4 particles can go into any these of 7 cells. So how many possibilities are there? 7 factorial. Total arrangement is equal to 7 factorial. 7 factorial means G1 factorial. So from here, for this first compartment, the total number of meaningful arrangement, that is equal to total arrangement G1 factorial divided by meaningless arrangement N1 factorial into G1 minus N1 factorial, right? So this is the total number of meaningful arrangement. I can write W N1, N2, so on Nk. So thermodynamic probability for the first compartment. Clear? Number of meaningful arrangement. So similarly, I can write down the same expression for other compartments. Clear? For second one, it will become here Z2 factorial upon N2 factorial into Z2 minus N2 factorial. Similarly, for third, it will become Z3, N3. Similarly, for kth, it will become ZK, NK, and so on for all others. Right. Now, if I write down the total number of meaningful arrangement for this entire macro state, what I will do, I will multiply all these terms. So I will get W is equal to G1 upon G1 factorial, sorry, it is not G1, it becomes Gi. So G1 factorial divided by N1 factorial into G1 minus N1 factorial multiplied by G2 factorial N2 factorial G2 minus N2 factorial into so on zk factorial divided by nk factorial into zk minus nk factorial. So this is now I can write it multiplication. I go from 1 to k gi factorial divided by ni factorial into gi minus ni factorial. Clear? So now let this is equation number 1. Clear? So now this is the thermodynamic probability. Clear? Right, for this macro state. Clear? So now I'm going to solve this equation, right? So to solve it, I will take natural log on both the sides. So log E W is equal to, when I take logs, it become summation Gi factorial minus log of Ni factorial minus log of Gi minus Ni factorial. Right. I go from 1 to k. So here I got not gi factorial, but it will be log of gi factorial. So I mistaken here. Let me correct it. Log of gi factorial. Clear? Log of gi factorial minus log of ni factorial. Right. So what is the next step? Now we are going to use a Stirling formula. So from Stirling formula, we know log of n factorial is equal to n log n minus n. This formula is valid when n is very large, right? So again, you will proceed in the same way as you did in the case of Bose-Einstein distribution law. You will, sorry, expand all these terms by putting this form of these terms, and then you will simplify these terms. Then ultimately you will arrive. I'm writing directly. I'm skipping 2-3 steps because we have did the same thing in the case of Bose-Einstein distribution law. So I'm writing log E W is equal to summation I go from 1 to k log E gi minus ni, right, minus log of ni into dni. Clear? So I got this equation. This so I goes 1 to k log of E gi minus ni minus log of ni dni. Now here I think I have mistaken one thing. So here the one thing that I have mistaken is this is actually d of log E W. Because we know after putting the Stirling formula and simplification, we take the differentiation of this side and this side, as we did in the case of Bose-Einstein statistics. So now d log E W is equal to this, right? Not, but here now we are going to apply the condition that for the most probable state, W is equal to W maximum, and so d log E W should be equal to 0, right? So here now I'm going to equate this is equal to 0. It is the same situation that we did in the case of Bose-Einstein statistics. So right here it becomes log E gi minus ni minus log of ni, that is into dni, right? That should be equal to 0, right? I go from 1 to k. Clear? Now this is the equation number 2. So once again, I am saying that from this step I have directly switched to this step. I have ignored two steps there, sorry. One is putting Stirling formula expansion and then taking the d differentiation of the sides. Then we arrive at this. Now again, we are applying the two conditions that we apply in the case of Bose-Einstein and Maxwell-Boltzmann distribution law. That is summation of dni is equal to 0 and summation of ei dni is equal to 0. This is equation number 3 and equation number 4. You know very well from where these two equation has been taken. It has been discussed in that lecture, right? So multiplying it by alpha and multiplying it by beta. Again the same thing. So it is alpha and it is a beta. And then what we will do? We will take the these two equation and we will subtract them from equation number this clear 2 equation number 2. So when you will subtract them, it will become summation of log of e zi minus ni minus log of ni dni minus alpha summation of dni minus beta summation of ei dni that is equal to 0. So what is the next step? It is quite clear that we will take summation of log of e gi minus ni divided by ni clear minus alpha minus beta ei into dni clear that is equal to 0, right? So again the same thing as the summation of I. Okay, these are independent of each other, so it means the term inside the bracket must be equal to 0. So it means right, so it means this term should be equal to 0. Log of gi minus ni divided by ni, right, minus alpha. So I can rearrange it. Log of gi minus ni divided by ni bracket is equal to alpha plus beta ei. Clear? So when I will simplify it, you can do it as we did in the case of earlier Bose-Einstein statistics. We will arrive at ni upon gi is equal to 1 upon e raised to power alpha plus beta ei plus 1. Clear? So this will be the distribution law, right? If I put the value of beta, that is 1 upon kt, right? Beta is equal to 1 upon kt. So then in that situation it becomes 1 upon e raised to power alpha plus ei upon kt plus 1. Clear? So this is the required distribution law for Fermi-Dirac statistics. Clear? So you can see here that this distribution law is telling us about the distribution of Ni particle into Gi sets, right? It is telling us this ratio, that on which factors this ratio depend. Clear? It is also called as occupation index. You can compare this occupation index for all three wings of statistics. Here it is +1, here it is -1, and here it is a no 1. Clear? So this is the occupation index or distribution law for this wing of statistics. Ni upon Gi is equal to 1 upon e raised to power alpha plus Ei upon kt divided upon not upon, sorry, plus 1 in the denominator, right? So this is all about this. Thank you very much.